alkanes. Okay, alkanes have got the general formula, which you use to work out the formula of an alkane, as CnH2n plus 2, right? Using this general formula, you can work out the formula of any alkane. So for example, if I said to you, oh, an alkane has got 20 carbons, there's an alkane with 20 carbons, how many hydrogens does it have? You can go, well, 20, so that'll be 2 times 20, 2 times 20 is 40, plus 2 will be 42. So you can work out how many hydrogens with a given number of carbons. Okay, but you actually need to know the names of the first 10. So if we go very quickly through the first 10, the first one is methane. Okay, 1 carbon. Then when you have 2 carbons, remember the general formula, 2 carbons, 2 times 2 is 4, 4 plus 2 is 6, C2H6 is called ethane. Then the next one, C3H8, is called propane. And then the next one, C4H10, is called butane. Now can you see what is happening each time here? Each one is increasing by CH2. CH2 increase each time as we're building up. And then C5H12 will be pentane. And then C6H14 will be hexane. C7H16 is heptane. They're all ending in ane because they're alkanes. Heptane. Then what we've got next, C8. Well, that will be octane. C9. And times 2, 18 plus 2 is 20. That will be non-ane. And then finally, C10. H22 will be decane. And you need to know the names of all of these alkanes. Okay, now this is called, this whole thing here, this is called the homologous, be careful with your spelling, homologous series of alkanes. And this is the word homologous series, okay, means a family of compounds with similar chemical properties, or you could say the same functional group. Okay, more about that in later videos. Same functional group with each member differing by CH2. So each member differing by CH2. Okay, it's called a homologous series. So this is a homologous series of alkanes. Right, so these, everything I've drawn here, everything I've written there, okay, all of that is called a molecular formula. And a molecular formula just shows you the numbers of each atom that is in the compound. Okay, so we know that there are 5 carbons, 12 hydrogens, 5 carbons, 12 hydrogens. So just the number of atoms of each element in a compound. Okay, the number of atoms of each element in a compound. Okay, now if we take, for example, pentane, for example, okay, pentane is C5, 5 times 2 is 10, 10 plus 2 is 12, pentane. Now pentane is 5 carbons in a straight row like this. Each carbon has 4 bonds. Carbon has to have 4 bonds. okay? And around each of these carbon atoms, the shape is tetrahedral, bond angle 109.5, right, around each carbon atom. If we took the simplest, if we took methane, remember how to draw your 3D shapes. Methane, tetrahedral, a bond sticking out, a bond going back and down. Okay, around each of these carbon atoms is a tetrahedral shape. Okay, what I've drawn there is I've drawn a displayed formula, because I've drawn every single bond. I've drawn every single bond is shown. When I'm saying bond, what kind of bond is it? What kind of bond? They're all covalent bonds. Okay, more information. They're actually sigma bonds, but I'm going to give more information about that when we talk about alkenes. Okay, sigma bonds. More information about that later. Okay, so their displayed formula. If I asked you for a structural formula, so there's lots of terms. This topic has got lots of terms. If I ask you for a structural formula, that's when you write the formula on one line. Okay, so that's when you write the formula on one line. That's how you know you got a structural formula. So this, for example, is CH3. So I'd go CH3, then I'd go CH2, then another CH2, then another CH2, and then a CH3, and that's called a structural formula. Okay, you can summarize it. You could go CH3, and because there are 3 CH2s, you could go CH2, 3 of them, because there's 3 CH2s, CH3. Okay, the last type of formula, so we've got displayed formula, we've got, that's molecular formula, just tells you the amount of each element, how many atoms. That's molecular formula, that's displayed formula, that's structural formula. The last type of formula is skeletal formula. Now skeletal formula is like a shorthand, because it takes ages to draw all this out. So it's just a shorthand, and you do not show carbon atoms or hydrogens joined to carbon atoms. You don't show carbon atoms or hydrogen atoms joined to carbon atoms. And because when we have a go, we're going to have a go at making this molecule. When you make this molecule, because of the tetrahedral shape around each carbon atom, it comes up as like a zigzag. So if we have one carbon atom, so I'm going to show a dot like that, a carbon atom, and then it's a zigzag shape to another carbon atom, and then a third carbon atom, and then a fourth carbon atom, and then a fifth carbon atom. So the end and the corner is a carbon atom. 1, 2, 3, 4, 5. Now when you're doing skeletal formula, you don't show the dots, you just go like that, a zigzag. And anybody seeing that knows straight away that that is pentane. Okay, pentane. And that's a skeletal formula. Okay, right, back to pentane. So pentane, if you have C5H12, okay, C5H12, pentane, C5H12, it could be like this. 1, 2, 3, 4, 5, right? It could be 5 carbons in a straight line like that. But C5H12 could be something else. It could be pentane, or it could be 4 carbons in a straight line with 1 carbon branching off. Okay? If I was to draw 4 carbons in a straight line and 1 carbon branching off there, that is still, this here is still pentane, because the longest chain without taking your pen off is 5 carbons without taking your pen off, and that is still pentane. But if I do 4 in a row and I put a carbon there, the longest chain without taking my pen off is butane, 4 carbons. And then I have to give the lowest number, because I'm going to number carbon 1, carbon 2. On carbon number 2, there is a 1 carbon methyl. Okay, so this chain, this kind of branching off, that is called a methyl. The general term is alkyl. It's called an alkyl substituent, alkyl group. It's 1 carbon, it's a CH3, it's hanging off the chain, so the name would be 2-methyl butane. Okay, and then could it be anything else? So if we put a carbon here, 4 in a row, and a carbon there, the longest chain is butane. Give it the lowest number. You can number from either direction, 1, 2. So it would be 2 hanging off, branching off, is a methyl group, 2-methyl butane. That is exactly the same thing. I've just drawn it in a different way. Okay, so far, just in summary, so far for pentane, for C5H12, we could have 5 carbons in a row, which is pentane. We could have 4 carbons in a row with 1 coming off, and that'll be 2-methyl butane. Okay, or we could have 3 carbons in a straight line with 2 carbons coming off, and that will be 5 carbons as well, and 12 hydrogens. The longest chain is 3 carbons, so that's propane. On carbon number 2, there are 2 methyls, and they're both on carbon number 2. So we have to go 2,2-dimethyl propane, 2,2-dimethyl propane. Right. These are all called structural isomers because they all have the same molecular formula. They are all C5H12 but have different structural formulas. Okay, we've already done the structural formula for this one. Here, it's CH3, CH2, 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 CH3. That's the structural formula for that. What's the structural formula for this one? For 2-methyl butane. Well, there's 2 methyls. Okay, so I'm going to go CH3, 2 methyls, 2 methyls, joined to a CH. Remember, carbon has to have 4 bonds. CH, then a CH2, and then a CH3. Okay, so it's a different structural formula. And then the last one, I've scribbled all over, it's not very clear. Let's do the last one on the new piece of paper. It's not very clear. So the last one was like this. Okay, 3 carbons in a straight row, and a carbon coming off, and a carbon like that. And this is a CH3, that's a CH3. Each carbon has to have 4 bonds. So there are 4 CH3s, and they're all joined to the same carbon. Okay, so that was propane, 2,2-dimethyl propane. Right, so they are structural isomers because they've got the same molecular formula but different structural formulas. All right, so next, let's go back to alkanes, right, and the homologous series, the family of alkanes. Okay, as you go down here like this, right, what happens to the boiling point? What happens to the boiling point, right? So the question is, as the chain length increases of alkanes, what happens to the boiling point? Okay, so here I'm going to give you some examples here. So the boiling point, methane is a gas, and it has a boiling point of minus 164 degrees. Okay, whereas if you take C4H10, okay, at room temperature that is still a gas, and that has a boiling point of -1. Right, the first alkane to be a liquid at room temperature is pentane. Okay, so carbon 1 to carbon 4, they're gases, and carbon 5 onwards are liquids. Okay, so as you can see, as you're going along, the boiling point increases. And why is that? Boiling point increases. That's because as you go along, the molecules have more electrons. Okay, remember when you're boiling something, if I take methane and another methane molecule, when I'm boiling it, I am not breaking the covalent bonds inside the molecule. I'm breaking the intermolecular forces. Okay, you're not breaking the covalent bonds, you're breaking the intermolecular forces. What's the intermolecular forces between methane molecules? Okay, well that's going to be the induced dipole to dipole forces, or London forces as they're called as well. Okay, so the more electrons that you have, the greater these forces are going to be. Remember that these forces are caused by an unsymmetrical, uneven distribution of electrons, because electrons are moving around the molecule the whole time, and there may be more electrons on one side of the molecule than the other. Okay, and this creates a temporary dipole, which makes a dipole in the neighboring molecule, which induces a dipole in the neighboring molecule. Okay, so if you have the more electrons, the greater the effect. So the larger the molecule, more London forces, or induced dipole forces, and therefore the higher the boiling point. Okay, there's another way to look at it as well. Another approach you can take is if you could talk about the surface contact, right? If you take simply like propane, and the propane molecules pack close together, okay? Whereas if you take something like 1, 2, 3, 4, 5, pentane, that's propane, C3. If you take pentane, like that, pentane, okay, there is more, there's a larger surface area. Pentane's got a larger surface area, and there are more points of contact. So there are more points of contact, and the London forces are greater, and therefore will have a higher boiling point. Okay, so that's increasing the chain length as the chain length increases. Now if you'd look at branching, okay, so if you compare, if you look at the branching, if you take, let's take this one here, okay, 1, 2, 3, 4, 5, pentane again, right, and you compare it with 2 methyl butane, again 5 carbons, or you compare it with the one we mentioned, so they're all the isomers. So this is the 2,2-dimethyl propane, okay, and this is increased branching. They are all C5H12, all of them, right? But there's more branching. Now, if you think about it, what's going to happen with the boiling point? So this straight chain can pack very close together, lots of surface area, large surface area, lots of points of contact, lots of London forces. This one will have a higher boiling point, okay? Whereas this one is like a spherical shape. So when it packs next to another one, there are very few points of contact here, very few London forces. This will have a lower boiling point. So the more branching you have, lowers the boiling point. Okay. Last thing I'm going to say, because this is just the start of alkanes, is where do alkanes come from? Where do we get alkanes from? They are very unreactive chemicals because the CC bonds, the CH bonds are very strong covalent. But where do we get it from? So we get a lot of our alkanes, or all of our alkanes, from fossil fuels. Okay, natural gas contains methane, amongst other things as well, and crude oil. Crude oil is a mixture of alkanes. And what needs to happen to crude oil in order to get the alkanes? Then we need to distill, and you have to do fractional distillation of the crude oil in order to get the mixture of alkanes.